Aquaculture is essential if we are to meet the world's growing demand for fish. Gravity cages offer a cost-effective and relatively simple approach to marine fish farming. However, these cages are susceptible to strong currents that can deform the flexible netting. This deformation reduces the cage's volume, directly impacting fish density, growth, and overall well-being. An accurate assessment of cage volume is therefore essential to determine the number of fish in the cage. A numerical model based on the finite element method was developed to calculate the cage volume. The implicit finite element method is applied and line elements are used to model the structure. A modified Morrison equation is used to calculate the load on moving slender structures. Full-scale experimental measurements were used as reference values. Two methods were employed to account for uncertainties, such as wake effects. In the first method, the cage volume is calculated without considering the flow reduction in the cage. A method used to estimate the drag force is then used to apply the flow velocity reduction. The nets are divided into upstream and downstream parts. The velocity of the flow acting on the downstream part is attenuated to a certain extent relative to the flow velocity of the upstream area. The loads on the nets are applied by adjusting the drag coefficient. The second method is used to calculate the model errors to evaluate uncertainties. The results are then used to adjust the numerical results. The first method of considering wake flow effectively reduced the differences in drag forces. However, it failed to reduce the differences between the remaining volumes from the physical model and the numerical model. In addition, when the reduction of the wake flow velocity used in the numerical model is too large, the calculated cage shapes do not match the observed cage shapes under experiment and field tests. A better approach to calculating the cage volume is necessary. In the second method, velocity-independent and velocity-dependent models are calculated. Both models can improve the numerical result and make it closer to the experimental result. The velocity-dependent model has much smaller sums of squared errors, which shows that it is a better method for characterizing uncertainty. This shows that the model uncertainty of the remaining volume depends highly on the flow velocity. The findings reveal that the numerical model, when corrected by these error estimates, provides a significantly more accurate calculation of the remaining culturing volume. This refined approach allows for more precise management of fish stocks. This method also considers the velocity of the water acting on the net structure, which enables a more accurate assessment of the cage's remaining volume.